Hello, everyone. Today we are going to look at a new topic. This is one of the first topics for Unit 9 called equilibrium reactions or reversible reactions. So I want to look quickly at the objectives of today's lesson, and then we'll get into what each one of those entails. So our first objective is we're going to be able to define reversible reactions. Hopefully this is pretty easy. The name's not too hard to understand, but we'll see what that means in the chemistry context. Then we're going to learn how to write reaction quotient expressions or Q expressions. I starred that because that is probably the hardest part of today's lesson. Hopefully you'll all be pretty confident in that though by the end of the lesson. And then lastly, we're going to try to understand something called an equilibrium constant, also called K or KEQ. So let's jump in. Okay. All right. So we've got reversible reactions. Up until now, when we've been talking about reactions, we've been talking about them as if they proceed in only one direction. The reactants become products. Here we've got this example of A and B reacting to form AB. I drew a particle diagram with A being the blue dots and B being the red ones. And these just come together, right, moving in the forward direction. Turns out most reactions aren't this simple, okay? In other words, once they form products, that's not necessarily the end of the story, okay? Right? So I want to look at this example. Suppose we did have a bunch of products that formed, okay? 3 molecules of products. Most reactions, in fact, in our bodies, it's almost all of the reactions, some of those products can go on and react to reverse the reaction, form the original reactants again, okay? So my question is, would this reaction ever actually stop if the reactants are able to make products, but the products are able to make the reactants? Okay, we end up with sort of this cycle, kind of a never-ending cycle, where we're constantly making products, but then we're using them up. And although the reaction never stops, it does eventually get to a point where there will be no perceptible change. We call this equilibrium. Okay, you've probably heard of the word equilibrium in some other context. Well, equilibrium is reached when the rate of the forward and reverse reactions are equal. Let me see if I can put this into simpler terms. Imagine if we had, say, equilibrium on a bus. What would that look like? Well, equilibrium on a bus could look like a constant number of passengers. That would mean if 10 people got off at a stop, 10 people would have to get on at that stop. That would be an equilibrium state. How about equilibrium in a bank account? Well, that would mean that for every dollar a person spent, they would have to earn $1 in order to keep their value, their total amount of money constant. In chemistry, it's when for every reactant that is consumed, a reactant is produced. The rates of the forward and reverse reactions are equal. The reaction is still happening, we just wouldn't be able to perceive any change because it appears as if nothing is happening. It appears as if there's no change. So let's look at how we actually can measure how far a reaction has progressed then. If we're not talking about reactions just proceeding from reactant to product and stopping, one way we could measure it, we can measure reversible reactions is using an expression called the reaction quotient. I started this because I said, this is one of the more challenging parts of this introductory lesson. Reaction quotients, symbolized as a capital Q, remember lowercase q is heat. Reaction quotients are defined as the concentration of the product over the concentration of the reactants. If you remember, a bunch of brackets, 2 brackets means the concentration of something. It's just a shortcut for writing concentration of something. Okay. So let's see what this could look like with some examples. I have 3 examples here that we're going to try. First one is A and B making AB, just like we saw in the above example. Okay. In this case, our Q expression Q would be the concentration of the products. The products here are AB, just one product, divided by the concentration of the reactants. When we have more than one reactant, we multiply them together. So in this case, I have two reactants, A and B. Okay, so this would be my Q expression. Okay, if you want, you can pause and see if you can try to do the second one on your own. I'll jump right into it. This reaction, two A's are combining to make an A2 molecule. Again, only one product, so the numerator is just A2. The denominator, though, is going to be A times A. Okay. Of course, we normally wouldn't write an expression this way, A plus A. How would we normally write it? We normally would write this with a coefficient, that is, two A's react to form A2. Okay. All right. So now, I could rewrite Q. What's a simpler way we can write A times A? We got A2 over A squared. Just want you to note 2A as a reactant ends up being A squared in my Q expression, not 2A. Okay, so coefficients from the reaction become exponents in the Q expression. We're going to try one more. Okay, these are all more or less the same. I would suppose this is the hardest of the three, but again, they're all more or less the same in terms of difficulty once you understand how they work. Then we've got Q, one product, NH3, that is ammonia, but there are two of them. So we're going to square that. Okay, the denominator, we have two reactants, N2 and H2. Just double check, do I have any coefficients? Yes, I do. So I'm going to need to cube the H2, okay? Yeah, the expression looks a little bit more complicated, but again, once you understand how it works, hopefully you'll be able to practice this in tonight's homework and it'll make sense. This is the main difficulty, I would say, for this first lesson, or yeah, first part of this unit. But once you've nailed that down, we can move into a little bit harder stuff. So let's try another problem. Let's use this one as an example. Okay, a 1 liter system contains 1 mole of N2 and 1 mole of H2 and no NH3. Determine Q. Okay, so Q is an expression that we could solve for numerically if we knew the values for each substance. And here we're given 1 mole of N2 and 1 mole of H2 in 1 liter. So those would both be 1 mole per liter. Q here is a pretty easy one to solve for. You'll see why in a sec. How much NH3 do I have? Well, I'm going to have to square it, whatever it is, but it looks like I have nothing. Okay, so 0 squared is, of course, 0. Really doesn't even matter what's in the denominator, but this would be 1 times 1 cubed, or 0. Okay, so for this system, Q is 0. That's because there are no products. And remember, Q is products over reactants. If we have no products, Q is 0. But Q wouldn't stay 0 for very long. What would happen if we were to wait? What would the reactants do if they're mixed together in a container? Well, they're going to react. We can't stop that from happening. When they react, the amount of H2 and N2 is going to go down. It's going to decrease, meaning the denominator is going to get smaller. And importantly, NH3 will not stay 0. It's going to increase. So over time, Q will increase. So Q increases over time. Okay. How high will it go? Will it continue to increase until it reaches 10, 100, 1,000? Well, turns out it depends on the reaction. Okay. So the value of Q will eventually reach some point at which equilibrium is reached. That is to say, the forward and reverse rates of the reaction are equal, and there's no more change. We call that the equilibrium constant at that point. Okay. So the value of Q when equilibrium is reached is called the equilibrium constant. And all reactions have their own values for K. And they vary based on the temperature, but they're unique to each reaction. So let's look at a quick example. If the reaction has a K value of 0.0043, that's actually the K value for the example we just did where nitrogen and hydrogen react. Okay, so it has a K value of 0.0043. Would there be more products or reactants at equilibrium? Well, if K value is quite small, like it is in this case, that means I don't have a very big numerator and I have a quite large denominator. Remember, the denominator is the reactants. Okay, so small K values mean that we have a lot of reactants left at equilibrium. Some reactions have very large K values, meaning that they predominantly make products if given enough time. So, quick summary of this would be to say, try to put all this on the screen at once, would be that if Q is less than K, that is when our reaction quotient is less than the equilibrium constant, the reaction is going to just continue to form more and more product until it reaches that equilibrium. And if Q is greater than K, then more of the reactants will form, and those products are going to continually react to be consumed and produce more reactants. But eventually, Q will equal K, and that's when equilibrium is reached. For this class, we're mostly going to be focusing on reactions in which equilibrium it has been reached. If you take an advanced class, you might see some problems where Q is not equal to K, but for most of our problems, I will simply say a system at equilibrium, and we'll be able to assume that Q and K are equivalent. Quick note, if we were chemical engineers or chemists wanting to make something, well, if we wanted to make a lot of products, okay, and this is something that a lot of chemists, that's part of their job, they want to make a lot of products, they want to keep Q small. As long as they can keep Q less than K, the reaction will continue to form more products. There are different ways they can do this. We'll talk about this in a later lesson. But one of the ways in which they can do that is to just continually add more reactants. As long as you can keep the amount of reactants in the system large, Q will stay small. Additionally, they could continually remove the products, trying to keep the concentration of products small, small, which will also keep K small. So just something to think about to see if you understand how Q is calculated. Just want to quickly jump back to the objectives. So our objectives today were for you to be able to define a reversible reaction. Hopefully you understand that. Reversible reactions are reactions that can proceed in the forward or reverse direction because the reactants form products, and the products also are able to react to form the reactants again. I didn't mention this. I did write it down, but they're noted with a double line. Reactants, double arrow. Okay, where reactants form products and products form reactants, this double arrow indicates a reversible reaction. Q expressions, I starred that. Like I said, I think those are the most challenging part of this this lesson. But those are defined as the concentration of the products over the reactants. Okay, we can use that to solve for Q at any given time. And lastly, to understand what that equilibrium constant is. It's a specific value of Q in which equilibrium is reached. Um, so an equilibrium constant, equilibrium expression, you'll hear me use that as well. Um, Really, it's the same idea as Q. It's just a specific value for Q. Okay, so equilibrium constant is the value of Q when equilibrium has been reached. Tonight's homework will have you um, practicing writing a few different Q expressions for some reactions. So hopefully that all makes sense. If you have any questions, please email me or leave a question on Google Classroom. Have a good one.